Okay, so moving on to a new topic. So this totally different than data mining. We're kind of leaving behind the idea of data mining in databases, records, fields, all those sorts of things. The next thing we're going to talk about for this class, the next kind of style or type of models that we can build, involve forecasting future values of a time series. So a time series is just like a very simplified data set. So where in data mining we have many fields of different types, categorical, numeric, and all of that. A time series is just a time-based set of values. So you have time maybe as one field, so maybe it's daily, today, tomorrow, yesterday, the day before, and then you have some numeric value associated with each day. Good examples of this might be, let's say, the stock price of a stock daily. It might be something like number of students in the class week by week. Okay, so if you have students adding or dropping, you might want to have a time series that say how many students were there each week throughout the semester or throughout the term, or things like that. And the whole idea of short-term forecasting is we want to predict future values. We want to say, is there a pattern to the historical values through time that we can exploit or learn something from in order to predict the next value in the future, whether that's tomorrow or next week or whatever it is. Now, you'll see as we go through, the algorithms that we have available to do this are only going to be useful to predict short-term future. That is, we may be able to predict tomorrow's stock price, but we're not going to be able to probably accurately predict next month the stock price or next year. Okay, the algorithms are only suitable for short-term, that is, near-term future events. So let's go through and start talking about them. Now, like data mining algorithms, we might ask, how are we going to evaluate which algorithm is doing better? Okay, so we're going to learn 4 algorithms. Some of them are just slight changes to existing ones. But we need to know, how do we measure them? How do we tell which one's doing better? And again, we're just going to rely on error. So we'll literally say, use the algorithm to predict the historical values themselves, and then take the difference between the prediction and the value we did have and see what that error is. Okay, so we'll do some sort of average error or some measure like that to say, how well did the algorithm do on the historical data, the past data, which would tell us some level of confidence. Do we think the algorithm is very accurate at predicting the future data? Okay. So essentially for all these algorithms, we're using past values, some pattern in them to predict future values. So the real difference between algorithms is, how do they weight, or how do they assign significance to the past values? Do they care about yesterday's value only? Do they care about all last week's values? Do they care about all values throughout the history? Okay, and how do they assign weight or influence to those how do they predict the next value in the series, the next sequence value? Okay, so that's really the only difference between these 4 algorithms we'll look at. And again, like I said, they're only useful to predict usually just one value in the future, or 1 or 2 values in the future. The reason is if you have to rely on historical data to predict the future, then if you want to predict further in the future, so if I'm using the algorithm to predict tomorrow based on today and yesterday and so forth, that's one thing. If I want to use that same algorithm to predict 2 days in the future, well, 2 days in the future, the history would include tomorrow, but I don't know what the value for tomorrow is yet. So I have to sort of predict tomorrow and then assume I'm correct in order to predict the day after tomorrow. So the further out in the future you go, the more you have to assume your prior predictions were correct, which is why these algorithms won't be very useful to predict far into the future, because obviously they're not going to be perfect. But we wouldn't have any better idea of what values to use between today, tomorrow, the next day, if we wanted to predict next week. Okay, so let's start talking about how we're going to measure the error between these, and then we'll look into some of the algorithms. There's So to measure error, we're going to take the actual value. So in my equations, I'll use v, and the subscript of t just means the value at time t. So that may be value 1, value 2, value 3. It may, whatever you want to assign meaning. Value today, value yesterday, value 2 days ago. And then we're going to make some prediction. So the algorithm is going to use historical values to predict something. The prediction we'll call p, or p subscript t. So we could use the algorithm to predict yesterday's value, even though we know yesterday's value. And then we can say between the real value, v, for yesterday, and the predicted value for yesterday, p, what's the difference? That is, how closely did we predict yesterday's value? And to measure error for multiple days or multiple values, there's 3 commonly used ways to do that. The first is related to what we talked about a little while ago with data mining algorithms, which is where we take the square of all the errors and then we average those. Okay, it's just called mean squared error. Okay, so literally we're just going to sum all the predictions we made, the difference between what we predicted and the real value for that time, square that value, right? Sum all of those up, add them up, and then divide by n, however many there were. So the average of the squared error, okay? It's mean squared error. The reason why you would square, of course, is because you don't want a negative error to offset a positive error. That is, if I under-predicted by, say, 10, and then the next time I over-predicted by 10, and I average those together, it would suggest that my average error is 0. Okay? So the squaring helps make every error that we sum up positive. Another way you could do that, using another approach, would be to just take the absolute value of the error. So instead of squaring it, just take its absolute value and average those. Okay? So that would be called mean absolute deviation. Okay? Now, I don't want you to get confused. Deviation just means error, right? It's just how off was the prediction from the real? How much did it deviate by? I assume the only reason they use deviation is so that the acronym comes out MAD, MAD. Okay, I don't know why they want it to be that way, but that's commonly what you'll see. Okay, again, it's just error. And then the last way we can measure error, which is a little easier to understand. So mean squared error is squaring values, so there's no unit to the error anymore. Mean absolute deviation, you can actually say, if I'm predicting, stock prices, dollars and cents, then the mean absolute deviation is literally the number of dollars and cents I was off on average, the average, amount I was off in dollars. However, you might want to change those, change the unit. Instead of saying how many dollars I'm off, you might want to say what percent was I off. That is, was I off by 10%, 50%, 1%? So if you do that, all you do is you sum up the error divided by the value itself. So the error as a percentage of the value itself, the absolute value of those. Okay, and we would call that mean absolute percent error. Okay, so mean absolute percent error is just on average how much percent was I off in my prediction of the real value. Mean absolute deviation is in the same unit as the value itself. On average, how off was I? If I'm predicting dollars, how off was I on average in terms of dollars? And then mean squared error really has no units. Okay, like we discussed earlier tonight, there's not a sensible way to interpret the value itself in terms of units and how off it was or what the error means. Now, why would you use one of these over the other? You might use one of these if you're trying to communicate how off or what your error was or how accurate your predictions were. It might be useful to be able to say mean absolute deviation. If I'm predicting dollars, I can tell you my average dollar amount that I was off in predicting. Okay, so on average, I predicted something that was $5 wrong, right? $5 higher or lower, one or the other. That would be mean absolute deviation. it might be more useful to communicate your error in terms of percentages. Okay, so I can say, hey, my prediction algorithm was only off by $5 on average. But if the values I'm predicting are something close to $5, that means I'm off by 100%, right? That sounds different, right? So sometimes you want to communicate the information in different ways. The reason you would use squared errors is, if you think about it, if I'm off by 1 and I square that, it's still just 1, right? If I'm off by 10 and I square that error, it becomes 100. So mean squared error will accentuate large errors, right? So you're averaging squared errors. If you're off by a lot, okay, then mean squared error is going to get very large very quickly because it's accentuating or squaring those large errors. So sometimes that's useful in telling you not just on average how off you were, but are you being off by a large amount versus small amounts? Okay. Now you can get some of that information in other ways, but those are some of the reasons you might choose one of these metrics over the other. In terms of this class, I've taught you all 3 algorithms. I will demonstrate all 3 algorithms tonight. In terms of assignments or exams, I would probably tell you I want you to use one of these metrics over the others. Or I want you to use 2 of these metrics and tell me what each one means or what each one tells us or reveals. Okay. So again, in the real world, you might have a reason why you want to communicate the information with one of these over the other. In this class, it's useful enough to learn them all, and we'll apply them all in different cases. All right, so let's talk about short-term forecasting algorithms. The first we're going to talk about is simply called the moving average model. There's only one parameter, n, and it just says I will predict a value by averaging the n previous values. Okay? So if I'm predicting tomorrow with a moving average with an n of 3, it means I will use today's value, yesterday's value, and the day before yesterday. Those 3 values, I'll average them together. That's what I predict for tomorrow. Okay? If I'm predicting yesterday, okay, so I'm going to predict yesterday and see how off I was using a moving average with n of 3, then I would use 2 days ago, 3 days ago, 4 days ago, average those together, and predict yesterday with that. Okay, so that's all that n means in a moving average model. Now you might choose a small n if you wanted to say, or if you thought that values maybe change drastically over time. So you might want to use a small n because it's not useful using last week to predict tomorrow. It's really only useful using today and yesterday to predict tomorrow. Okay? If, however, your time series is a lot more stable, that is, the values generally don't change a lot over time, but sometimes there's an error or something, or I wouldn't say an error. Sometimes there's a large spike in a value or a large drop in the value, but overall it's very constant, stable values. You might want a larger n so that those spikes or valleys sort of get averaged out over a large number of observations. Okay, so that's another craft skill that you kind of have to learn to apply through experience of different cases may call for different values of n. For this class, I'll tell you or give you the option to just choose an n to build the model. Any n will work, right? If I give you the option, you're free to choose anything you want. Okay. So literally, just the equation. So if I'm predicting p time t plus 1, so predicting some future value, t plus 1, I'll do that by taking the average at the current time, which means this today, or this value at the current time, the value before it, the value before that, the value before that, up to n of them, divided by n. Okay? It's pretty simple. Oops. So let's do an example of that in Excel. So I don't know what this data is. It's not important. But here's 10 values over 10 different time units. maybe those are days, weeks, years, wouldn't matter. What we do, we've observed some value for something over 10 discrete time units, and we want to use a model to say predict the 11th unit, so the next future value, based on this history. Okay, so using a moving average model, what I would do is I would compute some average and then use that to predict. Okay, and then the difference between what I predict and what I observed would be my error. Okay, so let's say, for example, let's make this a two unit moving average model. There we go. So every unit, or every time, I'm going to average the last two values. Okay, so I can't make an average at time 1 because I don't have two values yet. At time 2, I now have the ability to average two values together. Okay, so at time 2, I can average the values from time 2 and time 1 together to get a value, and then so forth. I can do that on down. Okay, so I'm just copying the formula so that each time it's averaging the value to the left and the value up and to the left together. Okay, and now I can make my predictions. Now the key is I'm going to predict time 3 the average I computed at time 2. Okay, so at time 2, I've observed a value of 106 along with a past of 73. I can average those together. That's what I will predict the value to be at time 3, is the value I averaged at time 1 and 2 together. Okay, so literally that's just a sort of delayed, right? Every average is the prediction at the next row and on down. So what that would mean is, for value at time 11, I would predict a value of 90. I think the next value in this series would be 90, okay, according to that simple model. Now I can also compute error and say, what's the difference between my prediction, so that minus the observed. So how off was I? So I can compute that for every time up through time 10. Right? I don't know what my error would be at time 11 because I don't know what value occurs at time 11. But I can at least tell you what value or how off I was from time 3 to time 10. Okay. Now, if I was going to compute one of those error metrics, mean squared error, mean absolute deviation, and so on, I might need to say take the absolute value of my errors. So let's do that. So literally just absolute value of the value to the left, and then I could average all of those together, and that would be actually, let me do it this way. Let me label it there and say that is mean absolute deviation. Okay, so just to help delineate what I've done here, I'm going to put a border around that and label it. So using a n of 2, averaging every two values together, okay, to make predictions, I got a mean absolute deviation of 17, meaning on average I was off in my prediction by 17. Okay, now that means something, but I don't know what these units are, so I don't know if that's dollars I'm off or number of people or what I'm predicting. It also doesn't necessarily tell me is that off by a lot or by a little, right? Something that would be more useful would be to say, what's the percent error I was off? Percent of the actual value itself. So I'm going to take each absolute error, divide it by the observed value, average those together, and that would be mean absolute percent error. Okay. So again, I'll put a border around that, label it so we can see what that is. I'll even format that cell to be a percentage. Okay. So, on average, I'm off by 17. Said another way, on average, I'm off by 20%. That is, maybe I'm under by 20% or over by 20%, but on average, I'm 20% wrong in my prediction. Okay. And just for fun, so this would be the absolute error percentage, and this will make error squared just to compute mean squared error. So if I take every error, multiply it by itself for every prediction I made, then I can compute the mean squared error. So the mean of all squares of the errors. Okay. And that's 406. Again, no units. Mean squared error is only truly useful if you're going to compare one algorithm to another. So let's do that. So I have a 2 moving average model given here. Let's go ahead. I'm going to put a border in between these so we can see it. Let's go ahead and compute a 4 unit moving average. Okay. So I'm going to compute an average, use that to make a prediction, and obviously I'll have an error as well. Now the key is I can't make an average of 4 things until I have 4 things to average together. So my first average can only be computed at time 4. Okay, and then from that point on, which means I can only make predictions starting at time 5. Okay, because a 4 moving average needs 4 things to average together. Okay, now I suppose you could average 3 things together for time 3 and 2 things together for time 2 and so forth. That's not really fair if you're saying you're using 4 units to make your, or 4 values to make your prediction with. So I'll only start making predictions once I have 4 things to average together. And I'll only measure that error from that point on. Okay. So again, I can compute absolute error percentage, and squared error. So the absolute value of each error, the fraction of the absolute error to the real value, and the error multiplied by itself. And then I can average each of those to get me the mean absolute deviation, the mean absolute percent error, and the mean squared error. Put a border around those. So now I have 2 models, 2 moving average models. The first uses 2 values in the past to predict each future value. The other used 4 values in the past to make each prediction. One more prediction. Okay. The first says, on average, I'm off by 17, which is 20%. The second says, if I format it, I'm off by almost 17, 16.8, which is still about 20% off on average. Okay. Mean squared errors, very close to one another. Okay. 406 versus 400. Suggests that both of these models are doing roughly about the same job at making predictions. That is, they're both fairly wrong or fairly right, depending on how you want to look at it. If 20% off is good for you, then you would say both models are doing good. If 20% is bad for you, right? Obviously, they're both doing bad. Okay, so it depends on context, but at least between these two models, they're doing roughly equivalent. Okay, you could try a moving average of 6. Okay, obviously with that you couldn't make predictions but for time 7 and on, and so forth. Any questions about a moving average model? Or any questions about the 3 error metrics, how they're computed, and how we would use them? Oh, question?
Is there any difference, like we have the AT column and the PT column, and it's the same value except down one. Is there any difference as far as where that, I guess, the benefit of having both of those columns?
Yes. So the question was, I created a column to compute averages and then a separate column to list the predictions, which is just the same column just shifted down by 1. The reason I do it that way, it's not the only way you could do it. Obviously, you can get rid of this PT column and just compute your errors as the last average minus the current observed and so forth. That'd be fine. I like to split them out because it's much clearer. You can visibly see how the model works by averaging some things and using that as your next predicted value. Okay, but you wouldn't have to do it that way. Certainly, you could format this spreadsheet in many different ways and get the same results. Yeah. Now, when we get to more complex algorithms in a minute, you'll see why it may be useful to compute some things and then compute your prediction separately, as opposed to combine them all at once. Okay. In other algorithms, we're going to compute multiple intermediate values, combine them in some way to make a prediction. So it'll become a little clearer then why you might want to use this format. But for this one, it's not critical by any means. Question?
So when you're defining what n meant, and then when you're defining what each of those error metrics meant, you use the variable n represents the number of items in the time series that we have, and not the number that we're using for the moving average.
Okay, so back to this equation here. N represents the number of items we use to make each prediction, not the total number of items in the time series. At least in this equation right here. Okay, so I'm using n values to predict the next value in this case. And so in my example here, my n was 2, and then later I tried an n of 4. Two different instantiations, 2 different representations of that same moving average model. I've just used a different parameter in terms of how many values to average together to do my predicting.
I think I might have phrased that incorrectly. I was thinking about the slide before that, defining the averages, writing the error.
Yeah, so the slide before this one, yes, I used n again. N here just means how many values did you predict that you're trying to average through. Yeah, I maybe should have picked a different variable here or a different letter. This just means if I'm adding together n different predicted errors that have been squared, then I'll divide by n because I want the average of the summed errors in each case. So n here is just how many predictions and values did you have that you're absoluting or squaring or whatever. Yeah, sorry about the confusion there.
No worries. I just wanted to make sure I was not asleep.
Two different intentions for the variable n. Okay. Pretty simple model. Okay. It will get more complex than that. The good news is it doesn't get terribly more complex. Okay. And the next 3 algorithms are all just extensions of each other. Okay. So we're going to kind of start with a simple one. We're going to add a little bit to that to make another one, and then we're going to add a little bit to that to make a third one, and those 3 will make up the other algorithms. Okay. Where moving average considers some amount of the history governed by your choice of n. Okay, it weights the influence the same. That is, if I choose an n of 4, it means I use the last value, the one before it, the one before it, and the one before it. But I'm averaging them together in such a way that they're all equally important. All right? I'm not weighting them different. I'm not saying the most recent value is more important to predict the future than the value before it, or the value before that, or so forth. So that's, in some ways, a problem, in the sense that most time series data, if it changes over time, it's more likely that your next value is closer to your last, most recent value than it is further back in the history. The further back in history you go, the less influence that maybe has in predicting the future. Okay? So, to address that, we'll come up with an algorithm, or we'll talk about an algorithm called exponential smoothing. Exponential smoothing technically uses all historical values. Okay? So you don't have to choose how many to use. It will always use all of them. But it will influence, or what you will choose is how much influence you want recent history to have versus ancient history, or history that's older. Okay? And the way we'll do that is through a parameter called alpha. Okay? Conventionally, most textbooks or tutorials on exponential smoothing use the value, or the term alpha, for this. Okay? And alpha is just going to be some fractional number between 0 and 1. And all it means is how much weight do you want to give the most recent value as opposed to all the values before it. So you might want to say, I want my prediction to be 50% based on the most recent value, and then 50% based on all the rest of the history. Or you might say, I only want my prediction to be based 10% on the recent value and 90% on the history before it. Okay? So you can use that alpha parameter to sort of shift how much influence recent values have versus historical values before. So here's what the algorithm itself looks like. Relatively simple. Okay, I'm going to predict time t plus 1 using a value, a smoothed value, we'll call it S, for the current time. So just like before we averaged and used that to predict the next one, we're going to compute a smoothed value and use that to predict the future. Okay, the smoothed value is just alpha multiplied by the current value, right? The recent value we have, and then we're going to add to that 1 minus alpha multiplied by the last smoothed value. Okay. Now, if you're curious as to why we call this exponential smoothing, you can actually take this S of t minus 1 and expand that out, because we computed that in the past, and it looked something like this, right? S of t minus 1 was just alpha times v t minus 1 plus 1 minus alpha of s t minus 2, right? So you can sort of recursively think about how all of these s values are influencing the next s value and the next one, right? But really, they're all just weightings of v values. So if you multiply that out, what you end up seeing is I'm going to predict the future by taking a recent value plus 1 minus alpha times the value before it, plus 1 minus alpha squared of the value before that, plus so on and so. So we're going to square and then cube and then take the 4th power and 5th power all the way up to the nth power for n historical values, all the way back to the beginning. So basically we're saying if alpha is a fraction between 0 and 1, 1 minus alpha is also a fraction. And all we're saying is we're going to take recent history and then discount the history before it, and then double discount the history before it, triple discount the history before it, on and on back until the beginning of time, or the beginning of our time series, which will be, discounted over and over and over n times by some fraction. Okay, so at that point you have a very small fraction multiplied by the first unit, okay, and a relatively small fraction a relatively large fraction multiplied by the recent unit. Okay, So that's where the exponential comes from, is we're exponentially increasing what the fraction we're multiplying by each historical value. All right, so let's see how this works as an example. Okay, because these two models basically came out looking the same, I'm just going to go ahead and erase one, and let's create an exponentially smooth model and compare that with the moving average model we had for this series of 10 values. Okay. Now, one thing we need to do is we need to decide what value of alpha are we going to use. So I'm just going to arbitrarily, for now, select half, or 0.5. Put a border around that so we know what it is. Okay. And I'm going to create the model such that it refers to this cell, so that we can change this cell to say 0.2 or 0.8, and it'll change all the numbers computed below. Okay. So the first thing we need to do is compute S. We'll use that to compute our prediction, P, and then obviously we'll do the same thing of computing all our various error values so we can compare the two models together. Okay. Okay. So to compute S, we have to start somewhere, unfortunately, right? So we obviously can't predict the very first value, but we do need to compute an S for it. And normally you'd compute S by using the value plus the previous S, but for the first time we don't have a previous S. So for the first S value, we just conventionally will use just the value observed. Okay. So obviously this is not our prediction. We can't predict the first unit, but we've got to start the algorithm somewhere. Okay. After that, we can actually start using that equation. Okay. So now the S at time 1 is going to be the alpha value. I'm going to make that an absolute reference. Alpha times the value at time 2. Okay. Plus 1 minus alpha. I'll again make that an absolute reference, times the previous S. Okay? So I'll leave that up there for just a second. So we're saying the S value, the smoothed value for time 2, is alpha times V at time 2, the observed value at time 2, plus 1 minus alpha times S from time 1. Okay? And because I've used absolute references to refer to the alpha value here, I can now copy this formula down, and every time it keeps referring to alpha in that one cell, but it refers to a new observed and a new S value for each row. Okay, so those parts of the equation change each time. All right, so now we can make our prediction, right? And our prediction really, simply enough, I'll start at time 3, because at time 3 we can make a prediction using our computed S from time 2. Okay. It's not really fair to try to predict time 2, because at that point we only have one value of history, and so I'm just going to leave that one off. Okay. So now I'm predicting again just using the prior S value, kind of like we did with the average over here, the A value. And I can compute error. So our prediction minus the observed. I can compute absolute error, just the absolute value of the error. I can compute absolute percent error, the absolute error divided by the value itself, the observed. And I can compute error squared, or error times itself, for each prediction. And then, like I did before, I can compute average deviation, average percent error, and average squared error. Okay? Format that as a number. All right, and what we see is, remarkably enough, the 2 moving average model and the exponential smoothing model, using an alpha of 0.5, by the way, have roughly equivalent absolute deviations, absolute percent errors, although mean squared error, it seems the smooth value is doing a little bit better. Meaning, right, on average it's off by the same amount, but when it is wrong, it's generally not wrong by as much. Okay, it's not averaging a large error with a small error. It's probably just averaging lots of equal errors. Okay, so it's getting a lower squared error than the moving average model. So if we were going to compare these two models, it's useful that we would have computed all 3 error metrics, because 2 of them suggest the models are equivalent. One of them suggests that one model is probably doing a little bit better than the other. Okay? So they're telling different stories in terms of what they're measuring and what they're comparing. Okay? So it's useful to have done multiple of them, or at least in this case the squared error, because that's telling us that one model is technically doing a little better than the other. Okay? However, now we can actually start playing with our alpha parameter. Because what we've said is with an alpha of 0.5 is to predict a value, we care about the most recent value to it with 50% weight, and every other value before that with 50% weight. No reason why that might be right. We might care a little bit less about recent values and more about the whole history. So we might choose a lower alpha like 0.25. Okay? Actually, before I do that, I'm going to copy these values so we have them to compare. So this was an alpha 0.5 that got us these values. So now let's try a lower alpha, maybe 0.25. Okay? And now we can compare not just the smooth model with an alpha of 0.25, but the smooth model with an alpha of 0.5 and a 2 moving average. And what we see is the lower alpha actually is doing better in all 3 metrics than the other 2. So it's a lower mean absolute error, lower mean absolute percent error, and a lower squared averaged error. Okay? So it seems like it's better for this particular time series, it's better to care more about the whole history than just recent history. Okay? I'm going to assume, let's record this and we'll find out. So I'm going to paste those, just the values. What if we used a larger alpha, like 0.75, right? Now, I don't know if you remember from last week, but a lot of times when you're making these kind of models, it's useful to think it through beforehand and predict what might happen. What do we think would happen with a larger alpha as opposed to the smaller alpha?
It's trending the same way, it'll probably be worse.
Okay. Intuitively, we think it will be worse, right? Because if lower alpha got us better, then presumably a higher alpha would make us worse. Let's find out. Seems to be the case, right? Higher alpha gave us a higher error in all three metrics. Okay. So now we've tried 3 different alpha values. We've recorded errors for each one, and we can use all those to make our conclusion about what a good model for this time series is. Yeah, question?
Yeah, so on the other hand, if we had a time series where we found that it converged to particular values, like let's say that we're trying to predict the temperature at the time of day, and we notice that it's getting warmer towards 3 p.m. in the afternoon, then it starts to get cooler.
Okay.
In that case, would a larger alpha value actually give us a more accurate prediction?
So let me repeat the question. So you're talking about if you had a time series, say the temperature at different times a day, there's expectedly a pattern that says it gets warmer up till about 3 p.m. or mid-afternoon, and then it starts cooling off again. And your question is, would a bigger or smaller alpha be useful for that? The direct answer to your question is probably a bigger alpha. That in terms of predicting how hot or cold it will be at one particular time of day, you probably care about times recent to that as opposed to earlier in the day, right? Because time or temperature is changing slowly over time, presumably. It's trending up in the morning and early afternoon, it's trending down in the evening, but it's not going to suddenly jump a large amount between, say, 1 hour and the next, or 1 minute and the next. And so you'd probably care more about the recent time series value than the whole history. That's the direct answer. The better answer to your question is there's a better model. Because exponential smoothing specifically doesn't notice that there's a trend that data is generally going up. All it knows is, based on the history, I'm effectively averaging values together. Right? I'm weighting some values more than others, but I'm still just weighting or averaging the history to predict the future. It's not necessarily accounting for, are our values always going up? Like, is every prediction underestimating because values are trending upward? There's actually a better model for that. So, good question. It's about 2 minutes too early, but good question. We're going to get right to that. Before I do that, though, let's graph this data. I think it'd be useful just to show what this data is going to look like. I never remember where they put this. There it is, insert. So let's insert, we'll do a scatter chart. So here's what the raw data looks like. Okay? So I'm just graphing the observed values over time. Let's add to this another series. Let's add our predictions using the moving average model. Okay, we'll even go 1 unit in the future. Okay, so that's what the moving average model says it's predicting at each time. Basically, what you'll see that somewhat looks like is just a delayed version of the blue line, right? So when the blue line started going up, the red line just sort of followed after it by going up. When the blue line went down, the red line did too, just a little later, right? It's just effectively mimicking the blue line with some lag. Okay. Now it's also averaging, so it's maybe smoothing a little bit. But let's look at the smoothing model. Actually, before I do that, let's use the better alpha that we had. So let's add another time series. In this case, we'll do the predictions there. Okay. So that's what the green line is, the exponentially smooth model. Okay. And what you'll see is, at least here with the low alpha value, it's taking that blue line and basically trying to smooth it out. That is, erase all the highs and lows and just sort of trend somewhere in the middle, right? Because a low alpha value means care about the whole history, smooth out the whole history, not just the most recent values, okay? So it's extra smooth, if you want to say that, for a lower alpha. Out of curiosity, so let's go back to the higher alpha and we'll watch what happens on the chart, right? So with a higher alpha, we're basically going back to, hey, just mimic the last value, right? So just look like the blue line delayed by 1, right? Because we're always predicting future from the past. So we're just literally mimicking the blue line with a high alpha. We're just slower at it, right? We're off by 1 time unit. We're skewed 1 time unit to the right. Okay, so the higher alpha is less smooth. It's more rigid, like the data is. The lower alpha, we can even go even lower alpha, say 0.1, is going to smooth out those differences much more. Okay, and just try to keep in the middle somewhere. Okay, when the blue line goes up and then down, the green line stays more stable through the center. Okay. Now, this particular data, if you look just at the blue line, just kind of seems to jump around. Sometimes it goes up, sometimes it goes down. on the whole, it looks like it's staying somewhere between 60 and 120 every time. Okay. The question asked was about something like temperature over the course of a day, which tends to trend upward and then downward based on the time of day. If you know you have a trend to your data, something like exponential smoothing, especially with a higher alpha, is always just going to be lagging behind, right? It's not going to know we're always going up. It's always just going to be a little underestimated each time. Moving average will have the same problem because both of those are just averaging the history to predict the future. So let's go back to our slides and talk about the next model. Yeah.
If on the moving average, the exponential smoothing approach, if we were to go for a much, much smaller time interval, would our lag or shift in the curves be so small that we would actually be closer than a smoothed out model?
Let me repeat the question because I'm not sure I understood it. So you were saying for the exponential smoothing model, if we had you said a smaller time series, or the difference in time is smaller?
More discrete intervals. So instead of like maybe every second, if we went every millisecond or something.
Okay, yeah. So smaller intervals between time. Yeah. So exponential smoothing is always going to have a lag. Mm-hmm. If you're lagging behind by a day versus you're predicting every second, so you're only lagging behind by a second, that might be better for you, right? So the granularity of your time series and the granularity of your predictions may come into play or may be important, right? Either way, you're always lagging behind by one time interval. Whatever unit that time interval's in, you're effectively always going to lag behind by one with both of the previous algorithms. So that's exactly what I'm saying here. So one criticism of exponential smoothing and moving average is you're always lagging behind. That is, if the real values are trending up or down, you're always going to either under or overestimate because you're always just lagging behind the trend. Okay? We can remedy that, okay, by adding an extra component to our model. So now we're going to have exponential smoothing like we had before, but we're going to add a component to predict the trend. So we're not just going to use a smooth value of the history. We're actually going to use information from the history that says, is there a trend? That is every time value always bigger than the time before it? Or is every time value always less than the time before it? If that's the case, then data is overall trending up or overall trending down. We should predict that and incorporate that into our prediction of the future. To make that trend prediction, we're effectively going to use exponential smoothing to do that. That is, if I care about if the last time unit was bigger than the time before it, more than I care about 2 time units ago being bigger than 3 time units ago, more than I care about 3 time units ago being bigger than 4 time units ago. So again, the trend over time we want to predict based on the history of the trend. So we'll use another smoothing parameter. In this case, instead of alpha, we'll call it beta. Okay. So here's what the algorithm looks like. So now our prediction, P, is based on 2 things. 1, S, the smoothed history. And 2, we're going to add to that this thing called T, trend. Right? We're going to predict the trend. That is, we think overall values trend up. So we just want to take not just the smooth value, but we want to add to that the prediction that, we're also all trending upward. So if we tend to trend up by 10 units every time, then our smooth value would tell us one thing, but we want to add to that 10 because we think overall we're just always adding 10 as a trend. Okay? So the smooth value is the same effectively that it was before. Okay? It's alpha times the current unit plus 1 minus alpha times really what you mean is the last prediction. Okay? So S plus T, because that's what we're using to predict now. Okay? So that's how we compute the smooth value. It's just I care about the current time value, and then every prediction I made before that, which incorporates every observed value in the history, right? Because again, it's exponentially weighted out. And then we're going to compute a t by saying we want beta times the difference in the smoothed values. Okay, so here we're saying I don't care about just the last value. I care about the difference between the last two units of history and really the last two smoothed values. Okay, plus 1 minus beta times the old trend, the previous trend. So that's exponentially smoothing the differences of smoothed values, which we're using as our indication of a trend that occurs in the data. All right, so let's go back to our example. Actually, I'm going to jump to I think it's this one here I want. So here's another set of time series data. Let's take a look, if we just graphed the data, what that would look like. Okay. Fairly jittery, okay, right? So it goes up, it goes down, it's kind of bouncing around. But you might say overall it does look like there's a trend going down, right? So values toward the beginning seem to be generally higher than values toward the end, right? So there's some indication that maybe values sort of on average go down over time. Now they still bounce up and down, but on average they seem to be trending downward, okay? So maybe we want to incorporate a trend into our model using exponential smoothing with a trend, okay? Now the good news is if there really isn't a trend to the data, then what you'll find is the t value generally comes out to be close to 0, right? If there's no trend, you don't need the t value. The mathematics would suggest it will just use 0 or something close to 0. So using the trend model, the exponential smoothing with a trend, isn't wrong even if your data doesn't have a trend. It'll basically tell you that. It'll basically come out working that your t values are always near 0, by which you know there's no trend. Okay, so we're going to have to compute s of t, t of t, and then use that to make our prediction. We'll call p. We'll compute error, and just for brevity's sake, let's just compute absolute error and use mean absolute deviation. All right, so as before, we have to sort of bootstrap or start our s value with something. So at time 1, we'll just set it equal to the value at time 1. Right? There's no history before that. Starting at time 2, we can actually use, well, before we do that, we need two things. One is an alpha value, and one is a beta value. Okay. I'll just guess for now. Let's use 0.5 for each of those. Okay. I have no knowledge that that's good or bad yet, but we'll find out. So again, our s value, same as before. What we do is we multiply alpha by the current observed value, so the value in column B, plus 1 minus alpha multiplied by the last s value. Okay, actually the last s value plus the last t value. Right? So basically we're saying we want alpha times the current unit or current data plus 1 minus alpha for what we would have predicted. Okay, which is the incorporation of all the history before the current time. And what we predict is always s plus t. So that's why we'll use s or c5 plus d5, s plus t here. Okay, so that gets us our smooth values. Okay, now these numbers will all change in a second once I start incorporating t values. So we also have the problem of we need to initialize our trend. That is, without any data yet, what do we think the trend is? Well, the easy thing is to just say, if I have no data, then I have no information. I have to assume there is no trend, so I'll start with a 0 value. Okay. Now, computing t. So computing t is exponentially smoothed. So again, we're going to take a beta, this smoothing parameter. Okay. We're going to multiply that by the difference of the current s and the previous s. Okay. And then we're going to add to that 1 minus beta multiplied by the previous trend. Okay. So we're exponentially smoothing the difference of s's with all previous difference of s's. Right? They're all previous trends. Okay. And we can again copy that formula down. So now we have our smooths value. So we're taking the observed values and just trying to smooth them out, right, by caring differently about recent history than the history before it. We're also smoothing out a trend that says, do we generally trend up or down? Okay. And again, we have a smoothing parameter, beta, in this case, to tell us whether or not we care about previous trend versus historical trend. And what you'll see, so initially, we have some negative values, maybe some positive. It seems like overall, right, we're generally predicting a negative trend. And there's times when we don't, because the values jump up and down. But overall, we tend to think maybe we're trending downward. And we do have values that aren't really close to 0. At least I see 4s and 5s, 3s. So there is very possibly a trend to this data. Now we can make predictions. So I'm going to start my predictions at time 3 when I have an actual S value, not just a starting S value, and an actual T value. Okay. So my prediction is always S plus T for the previous row. Okay. So that's my prediction, and I can even predict 1 out into the future. Now I can compute error as the difference in prediction and observed, and I can compute absolute error as the absolute value of that. Okay. And let's see. Looks like it's computing whole values for errors. I'm going to format that. Let's just say we want 1 decimal place. Okay. And there's no such thing as error in the future. Okay, so now we have a predictive model using smoothing with a trend. That is, we think there's a trend to the data. In addition to smoothing the history, we'll predict the trend and use that to predict the time series values. So let's add that to our chart. Let's see how that does. So expand this out, maybe make it a little easier to see. Yeah, let's go. There we go. So the blue line is the data. The red line is our smoothed model with a trend. Okay. And what you will see is, although there is some lag when there's these big jumps up and down, we do generally tend to stay close to the blue line. That is, we're not always over predicting as we might have otherwise, because we're calculating and figuring out that overall there's a trend downward to the data. Now, let's start playing with alpha and beta. Okay, so alpha says how smooth out do we want to make this curve. The higher the alpha value, the closer the curve will look like the real data. That is, the more jumpy it'll be. The lower the alpha, the more smoothed out it'll be. So let's go with the lower smooth or lower alpha. And there again, so what you'll see is we're kind of smoothed out all those valleys and mountains, the hills up and down that bounce up and down. We've smoothed them down. Beta will tell us how much we try to keep track of the trend, right? So if we take a very low beta value, let's say even just 0.1, what you'll see is we've basically shifted that red line up, right? Because again, the blue line seems to trend down. If we assume, a low amount of information about the trend, that is, we don't really care about recent trend data, we'll just average out all trend data, right, over time, then what we tend to do is we tend to lag behind the trend, okay? Or it takes us longer to figure out that there is a trend. If we take a higher beta value, let's go all the way up to 0.9, what you'll see is we've shifted down, but we've also sort of counteracted our smoothing a little bit by figuring out that, hey, sometimes this graph jumps by a lot, right? And when it jumps by a lot, our recent trend says that obviously this thing's trending upward very quickly sometimes, and then downward very quickly. So now our red line tends to jump a little more because it picks up on those immediate trends, those immediate points that jump up and jump down. Now, is there a right and a wrong answer? Depends. How you would know is to use error metrics. Mean absolute difference, mean squared error, mean absolute percent error. You can try, like we did before, different alpha and beta values, and then capture what your error metrics are, one or all three, right? And then you would just look and say, which one is getting the lowest errors, right? Do I need a higher alpha? Do I need a lower alpha? Do I need a high beta? Do I need a low beta? It depends on the data, obviously. This data, I would say, has a trend, but it also has, a lot of volatility. There's a lot of times when the trend is bucked or refuted, and instead of trending down, the value suddenly goes very high, right? And then goes down again. So while there might be a trend here, it's a very subtle trend with a lot of variability, volatility. So that might suggest you want maybe a higher alpha, maybe even a higher beta. Okay? You'd have to try and see. All right, questions about trending? Yes.
So let's say that we were trying to do something that might have a lot of volatility to it, like predicting stock market prices or something.
Okay.
Would one way to counteract the effect of those sudden inflection points be maybe use a moving average to try to hedge your bets and say it could suddenly shift the other way or something like that?
Yeah, so the question was, if you have a time series that is very volatile, say stock prices, which for some stocks, jump high, jump low across a given day, whether you would want to use maybe something like moving average so that you can so that you smooth out those jumps in a different way, right? So you basically average the volatility with the stability over the last week or whatever your moving average window is. Yeah. That's one way to think about it, certainly. Yeah, follow on.
I just wanted to clarify. I was thinking maybe could we use something like this with the trending in order to try to predict which way we think it's going to go, but then let's say we're buying futures on this, but then we're shorting stocks with moving average just so we're kind of like a hedge fund.
Okay, so basically you're asking, is there a case where you'd want to maybe combine both this trending approach and the moving average? And yeah, you can certainly combine some of these approaches. There's not we won't try in this class, let's say, but certainly you can take any number of things. We're going to look at one more algorithm that adds one more layer of complexity that you can either opt in to using or take out. Maybe you predict trends, maybe you don't. You can combine these in different ways, certainly. These are algorithms that I'm showing you are kind of the standard ones, right? That's the sort of simple, straightforward ones. You can certainly combine them together in different ways. Maybe you sort of average together a moving average and an exponentially smooth model, right? To sort of get some sort of blend, let's say, of the advantages of both. You could do something like that. What it will always come down to is your error metrics. Obviously, the only thing we really care about is predicting well or accurate, which is governed or measured by your error metrics, right? So as long as you can reduce your error by combining approaches or adding more complexity or maybe taking some of this complexity away, that's the right answer. That's what you should do, because what you want is lower error, which means more accurate predictions. Okay. One more model for tonight. Now, beyond a trend. So maybe the data trends up, maybe it trends down. Some data series or time series actually exhibit a cyclical pattern. For example, temperature over the course of a day tends to go up in the morning, or between the morning and the afternoon, then tends to go down between afternoon and evening. That pattern repeats. Tomorrow it will probably do the same thing. The day after it will probably do the same thing. You'll always see this pattern of going up in the mornings and early afternoons, going down in the late afternoons and evenings and night. Okay, that would be a cycle in addition to, a trend, maybe. And so we can try to account for cycles in addition to smoothing the history, in addition to predicting and smoothing the trend. We might want to measure cycles. Okay. Now, measuring cycles will involve two things. One is a smoothing parameter. Okay, so again, we'll take sort of recent cycles and historical cycles and blend them together and smooth them with a parameter like we used alpha and beta. Now we'll use one called gamma. But in addition to that, we also need to know how often or how long does it take the cycle to repeat? How many time units go by before the cycle starts over again? So in the sense of our temperatures, the cycle repeats every day, right? So every day the cycle repeats where you start trending up till about 3 p.m., then start trending down till the next day starts, and then repeat. In terms of other things, you might have yearly cycles, things that are based on, say, season of the year, summer, fall, winter, and spring. Maybe you're selling swimming suits, or maybe you're selling jet skis. You'll probably sell more of those in the summer, right? When people tend to wear bathing suits and ride jet skis. Probably not going to sell as many of them through the winter and spring. Year by year, you'll see a pattern, a cycle repeating, where that generally sales go up in the summer, sales go down in the winter, right? So you have to know what that periodicity or what the length of those cycles are. We'll call that P in terms of the equations we're going to use. Okay. So now we have exponential smoothing, we have trending, and now we're going to add cycles. Okay. So here's the equations. Now, I will say the book goes into this, but I'm not going to, just for brevity of time. You can certainly do exponential smoothing with a cycle and no trend. That is, you can just take the t value out of these equations, okay, and just have a smoothed value and a cycle. That's fine. Again, it's just blending these approaches in different ways, right? You can add in and take out some of these approaches or some of these methodologies. Here's the equations if you were going to smooth with a trend and a cycle, okay? Now, the book talks about two ways to do that. One is you can add the cycle in, like you're adding in the trend. The other is you can multiply the cycle. So you can make the cycle sort of a factor that you either multiply or divide to say overall, summer sales go up by 10%, down by 20% for the winter. That's in terms of, a factor that you're multiplying or dividing out. Here's the equations if you were just going to add values in. I find this more straightforward to implement because, as you'll see, it's going to look very similar to all the other equations. If you're interested in the multiplying way of doing it, you can refer to the book or online. In terms of class, I don't care which one you use. If you want to learn both and pick one, that's fine. Like I said, I find this one a little easier to understand and explain. So again, our prediction is just going to be the smooth value S plus the trend value T plus now a C value for cycle. The key is where you're predicting the future based on the recent smooth value and recent trend, you need to base that on a cycle that was p time units back. Okay, so again, if I'm going to predict values for noon, or temperatures for noon today, the cycle part of that I care about is noon yesterday, right? So I need to go back 24 hours. That's the period P that the cycle repeats. Okay, so whereas you use ST and TT, you're going to use a C value from basically P time units before the one you predict. So T plus 1 minus P is the place you want to look for your cycle to predict a value at time T plus 1. All right, so S, same as before. The only addition now is, of course, when we smooth our V value, we need to subtract out the cycle, okay? Because we want to smooth the values themselves without the cycle being included, right? Whatever the cycle we think is, we want to smooth the raw values, okay? So V minus C. T looks the same as it did before. We're just using beta to weight the difference of S's with old T values. And now we can compute a C value, okay, which is going to be the same as exponential smoothing. We use gamma as our fraction. And what we're smoothing is the difference between V and S, okay, with old cycles from P time units ago. So again, your cycle you're adding in, or you're smoothing here or adding into your prediction, is always going to be based on P time units ago, not 1 time unit ago. Okay, so it matters what value for P you choose. Obviously, you have to know how often the cycle repeats in order to predict it. Okay. Now, the reason we use V minus S obviously is what I care about when I say cycle is what's the difference between the smooth value and the real value. That is, if I'm predicting temperature at noon, then I care about the smooth value of temperatures up to noon, right? But I also need to take into account what value does noon generally have, based on noon yesterday, the day before, and so forth, right? So I need to sort of, when I'm computing cycle, I need to when I'm computing cycle, I'm doing the difference between just the smooth history and the value itself. When I'm smoothing the value, I've got to subtract out that cycle, okay? So I got to take away the cycle to smooth out the history, because the cycle is the difference between the history and the smooth value. And then I'm adding in the cycle to make my prediction, okay? All right. I maybe didn't explain that very well. You can just trust the math, okay? The equations are what they are. So let's do an example. So let's take this time series here. We'll start by graphing it. It's a long time series. So let's make a cycle. A graph. That up. Okay. And what you'll see, what it looks like is happening, right? One is there's a trend, okay? Discounting whatever seems to happen here in the middle, it seems like there's a general trend upward, right? There also seems to be a cycle, whereas after, what is this, 0.9, 0.10, after 10 units, we drop down. After another 10 units, we drop again. After another 10 units, we drop again, right? So there's some cycle being repeated here that after every 10 time units, we've trended up, we're going to kind of reset down again and then start trending up again. And then we're going to drop back down again. Somehow, maybe there's 2 cycles going on here, but it looks like after the 60th time unit, we have a large drop, and then we start repeating with smaller drops again. Okay. Maybe there's 2 cycles. I'm not sure. Let's not get too concerned with that. But let's assume certainly it looks like there's a cycle being repeated in addition to a trend. So let's use the exponential smoothing with trends and cycles. Okay. So we have our S, T, and now our C values used to make our prediction. So again, as always, we'll initialize S to the value itself. We'll initialize T to 0. And now we need to decide something. First, we need to decide we're going to have an alpha, a beta, and now a gamma value. Let's, again, assume all those are 0.5. But also for our cycle, we need to know how often does a cycle repeat. It appears as though every 10 units the cycle repeats, right? So we're going to use P, the lowercase p, our periodicity, to be 10, okay? What that means is we have no cycle for the first 10 units, okay? So for the first 10 observations, we have no information about a cycle, kind of like we have no information about a trend for the first one. Only once the cycle starts over for the first time can we start computing the cycle. Because again, cycle at time 11 is going to be computed based on cycle at time 1, 10 time units ago. Okay, so this is how we have to initialize a smooth value, a trended value, and now a cyclical factor. Okay, so smooth value, same as always. I'm going to take alpha times the data value plus 1 minus alpha times the S value plus the T value. Okay, make sure that's right. Okay, so alpha times, oh, I'm sorry, I did forget, V minus C plus 1 minus alpha S plus T. So this should have been V minus C, okay? So the current cycle, okay? Oops, go back. I'm sorry, not the current cycle, the cycle P time units ago. So the current value in the cycle from P time units ago, okay, and so forth. So that's the reason I started there. So we don't have a cycle for the first time 10. We don't have a cycle 10 time units ago for the first 10 time units, right? So that equation will hold up through here. And then what we need to do is modify it such that we take alpha times the current time unit minus the C from 10 time units ago. So at time 11, we need to subtract out the cycle from time 1. Okay. So that's just the equation we saw on the slides. Multiply that, or copy that down. We can do trends. So trend is beta times the difference of S values for the last 2 S's plus 1 minus beta times the previous T value. Okay, so we're just exponentially smoothing the difference of each pair of S values over time. Okay. And now we can start computing C as well. So let's go back and review that. So C is gamma times the difference of V and S plus 1 minus gamma of the C from P time ago, not 1 time unit ago. Okay. So gamma times the difference in the observed value and the S value plus 1 minus gamma times the cycle 10 time units ago. So 10 rows above. And now we can start making our predictions. Now, we can only, I would suggest we only start making our predictions, at time 12 after we have a known smooth, trend, and cycle value. Okay? So our prediction is literally just the smooth value plus the trended value. Sorry, I did do this wrong. So the smooth value plus the trended value plus the cycle value from 10 time units ago. So at time 11, we have at least an assumed cycle from time 1 we can use. And then, of course, we can always compute error. And we could use that to compute mean squared error and other things. Okay. So let's add in our smooth predictions. Actually, we need to predict. We can even predict 1 unit out in the future. So let's see what that looks like. Going to move this to a new sheet. There we go. Makes it a little easier to see. So, what we can see is our red line, the prediction, seems to start, predicting a little high, right? So it sees that there's a trend. It's trying to incorporate that trend. Seems to take a little while before it actually realizes that it was overestimating the trend. But it does seem, so between this cycle and this cycle, as you can see, by the time we repeat the cycle maybe for a 4th time, maybe it's really starting to understand what the cycle is. Now, not sure what happened here. Seems like we've gone somewhere wrong. But it is trying to at least follow the pattern. I'm going to bet I have an error somewhere, that it suddenly dropped here. See if that makes sense. Prediction is S plus T plus C 10 time units ago. Okay. C is gamma times the difference of the value in B, the smooth value in C, 1 minus gamma times. Yeah. Alright. I think that's correct. So, obviously, we have this chart based on these alpha, beta, and gamma values. So we might want to start playing around and say, do we want to heavily smooth? Do we think the trend, changes very often? And how important or how often does the cycle seem to, or not how often it repeats, but how much of a cycle is there? So we may want to actually try a lower gamma value and let's say a higher alpha value, right? And now definitely changes the look of the chart, right? Because now we're smoothing things out a little more, but we're also changing the way we handle cycles, right? How much we care about a recent cycle versus a historical cycle. Now, what seems probably to happen, if you'll notice, so we trend upward, but how far the cycle drops us back down seems to also go up. Okay, so that drop seems to trend higher and higher. It actually goes very high at some point, and then it kind of starts over. Obviously, those are factors in determining how we make our predictions. You might find that you could add in another cycle parameter, another C value, that's not based on a cycle repeating every 10, but maybe every 60 time units or something else, right? to incorporate the fact that really it looks like there's one cycle going on here, but then something else that happens in the middle, maybe that would happen beyond, that we should take into account as well. And we can continue playing maybe a higher or lower beta value, change how we trend, and so forth. Oh, you know what? I know what the problem is. Or at least I know why that looked so funny. It's because I didn't take into account that we're predicting starting at time 11. There we go. Much better. Thank you. So we can't make our predictions obviously at time 1. We can't start making them till time 11. So I had my red graph shifted to the left a little bit. So now you can see how we're making our predictions. And what you can see is really by the end, we seem to be doing very well, right? I mean, we're not lagging behind, or if we are, it's not by very much. We seem to have figured out the pattern, right? That there is both a trend, data's going up over time, but then every so often there's a cycle that causes it to drop back down. Okay, so now here in the middle, you'll see there's probably a pretty big error at this one time unit, okay, where we didn't quite figure out what that big drop was going to look like. But we quickly recovered, right? You can see actually it caused us to go way down below here before we sort of recovered and started figuring out again, okay, the pattern is back to maybe its normal state. All right, any questions about cycles? Like trends, so what you'll see is if you applied this algorithm to data that either didn't have a trend or didn't have a cycle, T and C values should just naturally come out to be 0 or close to 0. Excuse me. And what you'll really see, actually, let's go ahead and graph C values. You can see what they look like. So again, this cycle factor is saying how much do we need to add to the smooth trended value to account for the fact that there's a cycle. And so what it's finding is it's kind of blending information with a trend, but what it's saying is you don't need to add much to the smooth trended value except for every 10 time units. And every 10 time units you need to subtract a big value, right? That's what the cycle says, is every 10 time units there's a big drop. So just graphing the C values basically tells you that, shows you that. Now it's also saying maybe over time you need to be adding more and more. What that says, right, if you go back and look at the data, at least the blue data, right, it trends up, then drops. It trends up a little faster, then drops a little more. It trends up even faster and then drops a little more, right? That's exactly what your C values are telling you here. Initially, we don't know anything to add, right? But we do know every 10 time units, right, we're subtracting more and more. And over time, the values in between every 10 time units, you're adding more and more to them. That is, there's a trend, but the trend is also trending, right? That every time the cycle repeats, you need to grow faster and drop more. And it repeats again, you need to grow even faster, drop more, right? So you can see that pattern spelled out in the graph of the C values. Okay. Obviously what we did not do here is compute an error metric and compare it to another algorithm, or an algorithm with different parameters, different alpha, beta, or gamma values. That's probably what you would do in the real world, or even on the assignment, okay? Is not just create a graph or create a model, look at the graph. You create multiple models with different parameters, measure their error, and figure out which one's doing better, right? And then maybe graph the better one to see visually how it does, and visually, how it's going to make predictions. Okay. Any questions about short-term forecasting?
Could we use Excel, like Solver or something, to basically optimize the values that are chosen?
So the question was, could you use Excel or this analytic solver platform to optimize like alpha, beta, those parameters? That is a great question. Yes. We haven't talked about how to do optimization yet. That's going to be the next topic. Once you learn that, absolutely. You can take that and come back and say, okay, now I have these parameters, and presumably there's some setting for them that's optimal. That is, that achieves the minimum lowest error achievable. Okay? How do I find them? Optimization will actually do that for you. There's different kinds of optimization. We'll see that over the next 3 or 4 weeks. Some of those types of optimization can't be used for some of these error metrics, while others could. So we'll kind of see how that works. But absolutely, rather than just guessing alpha, beta, and gamma values, which is what I'll ask you to do for now, eventually we're going to learn some techniques that would tell us how do you optimize and find the absolute best ones to minimize your error. Now you have 3 error metrics. You may minimize one that doesn't minimize another one, right? Because they measure different kinds of things, but at least you can minimize something. All right. Rather than take a break, let's just end class. So, rather than come back and talk about linear optimization, we're close to out of time anyway, so we'll just pick up linear optimization starting next week, which is fine. Next week, I am actually going to be out of town, so you don't need to bother coming here next Thursday. You're welcome to. You won't see me here next Thursday. I will pre-record a lecture, post it online, talking about linear optimization. Okay. The way we're going to start talking about linear optimization is we're actually going to do the math by hand, like on the whiteboard or pencil and paper. It's a little bit tedious, but it helps you understand why it works and how it works when we start using it in Excel. And certainly, we're not going to do real hard problems by hand, whereas Excel we can use to do very complex problems. Okay, but that's where we're going to start next week, is linear optimization by hand, pencil and paper, graphing things, something like that. Since I won't be here next week to talk to you about it, I'm going to go ahead and talk about the midterm. So the midterm won't be next week. Obviously, I won't be here. It'll be 2 weeks from tonight. Okay, so the 4th class will have a midterm. The way the midterm will work is you'll just come to class normally, 6 p.m. We'll start the midterm. Okay, so I'll pass it out. It'll be pencil and paper. The midterm will cover data mining, short-term forecasting that we just did, and linear optimization by hand. Okay, so really those 3 topics. Since it's a pencil and paper exam, I obviously can't ask you to run a data mining algorithm, right? What I would ask you is, why do we partition? Or how do you measure, or how can you tell whether one data mining algorithm does better than another one? Okay, and you would say something about errors or something about lift charts or something. I might even ask you on the exam and give you an example lift chart for 2 different data mining algorithms and ask you to tell me which one do you think represents the better algorithm that is more predictive or better at predicting, okay, and why. So you would have to talk to me about how do you interpret a lift chart to determine which one's doing better, okay. Same thing for short-term forecasting. I'm obviously not going to ask you to forecast 100 values, okay, or a time series with 100 values. Do all that by hand on the midterm. What I would ask you is things like, what are the 3 error metrics? Okay, so mean squared error, mean absolute deviation, mean absolute percent error. I wouldn't ask. I don't want you necessarily to memorize the equations. Okay, so I'm not going to ask you what's the equation to compute mean squared error. Okay, what I might do is actually give you a small set of data and ask you to compute it, but I'll give you the equation. Okay, so I don't necessarily want you memorizing equations. I'd rather you learn how to use them or what they mean. Okay, so I might ask you why you might use mean absolute deviation over or versus mean squared error. Okay, and kind of talked about what they measure and how they differ. Specifically, whether you're wanting to communicate information or whether you're wanting to try to measure, variability of errors or something like that. Okay, that's what I would ask on the midterm. In terms of what we'll cover next week in the video lecture, linear optimization, I'll likely give you a linear optimization problem on the midterm. Okay, you don't know what that means yet. You'll know next week and through the assignment for next week, but that'll be something you'll just compute several things by hand using some equations that will be given to you on the midterm pretty much. Okay, and that will be it. So the midterm will be 2 weeks from tonight. It will likely be either 1 hour or 1.5 hours. Okay, so it won't last the whole class period. There'll be a cutoff time, and I haven't determined it yet solely because I haven't written the midterm yet. Once I've written it and figure out how long it is, I'll set a time limit. So do be on time 2 weeks from tonight so you can start the midterm, because there will be a cutoff time. After that, we'll just move on talking about a new topic. Likely we'll start talking about linear optimization in Excel itself. Okay, so that'll be 2 weeks from tonight. So you might start getting prepared or start thinking about that. Don't forget that assignment 1 is due tonight by midnight, 11:59, whatever. I am not so strict that if you turn it in a little after midnight, it won't be accepted. Okay. What I don't accept is if you turn it in tomorrow at noon, right, or tomorrow afternoon or mid-morning or something, right. You have to I want it done tonight, by tonight, submitted by tonight. Okay. Generally speaking, I don't take late assignments. Again, I don't mean late by 3 minutes or even 10 minutes or 30 minutes. I mean late by hours. Generally, I don't take late assignments, okay, just as policy. So don't forget to turn that in. I will post to Blackboard the lecture videos from tonight, as well as assignment 2, okay, which will cover short-term forecasting. So I'll ask you to, in Excel, create some short-term forecast models of the different algorithms we studied, maybe compute some of the error metrics, and then answer some questions about which model does better on a particular problem according to those error metrics. Okay, I'll post all of that probably tomorrow morning. Okay, so you can get started on that. It will be due next Thursday. Okay. Unfortunately, we won't get to review it since I won't be here in class. Okay, so definitely don't put off working on assignment 2 to the last minute. Because I'll be out of town, I may be less responsive to email. Okay, I will still do my best to check email every day, respond to questions as fast as I can, but I would encourage you to start working on assignment 2, tomorrow or this weekend, as opposed to next Wednesday or Thursday. Okay. Any questions about any of that? No. Okay. Well, thank you very much.